Hello class, in this video I'll be introducing the second derivative test and how it can be used to identify relative extrema. Let's begin. The second derivative test states the following. Let the second derivative exist on some open interval containing c, except possibly at c itself, and let the derivative at c equal 0. If the second derivative at c is greater than 0, then f of c is a relative minimum. If the second derivative at c is less than 0, then f of c is a relative maximum. If the second derivative at c is equal to 0, or the second derivative at c does not exist, then the test gives no information about extrema, so we must use the first derivative test. Now we want to make a note. The second derivative test does not work for those critical numbers c for which the first derivative at c is undefined. When the first derivative at c is undefined, then the first derivative test must be used. Now to help you visualize what the second derivative test is saying, I'm going to show you a graph. To obtain a relative maximum, the graph of a function must increase, then decrease. This means the graph will be concave down, and the second derivative will be less than 0. In order to obtain a relative minimum, the graph must decrease, then increase. When this occurs, the graph is concave up, and the second derivative is positive. Now let's take a look at an example. For example 12, we want to use the second derivative test to determine any local extrema for the function f of x. To do this, we're going to need to find the critical numbers using the first derivative, and since we're applying the second derivative test, we're going to need the second derivative. I will start by finding the critical numbers. To do this, we need to determine where the derivative is equal to 0 or where the derivative is undefined. So I'm going to set the derivative equal to 0 and factor out an x from both terms. So either x is equal to 0 or 15x minus 6 is equal to 0. For the equation on the left, there is nothing to solve. We just have x is equal to 0. For the equation on the right, x is equal to 2/5. The domain of f of x is all real numbers because f of x is a polynomial function. Since 0 and 2/5 are in the domain of f, we can conclude that they are critical numbers. Now to determine where the derivative is undefined. Since the derivative is a polynomial function, the domain is all real numbers. This means that there are no values of x that make the derivative undefined. So the only two critical numbers are going to be 0 and 2/5. Now to apply the second derivative test to determine if the critical numbers are relative minimums or relative maximums. I will start by testing x is equal to 0. When x is equal to 0, the second derivative is equal to 0 minus 6, which is equal to negative 6, which is clearly less than 0. By the second derivative test, we can state, since the derivative at x is equal to 0 is 0, and the second derivative at 0 is less than 0, there is a relative maximum at x is equal to 0. The value is f of 0, which is negative 3. Next, we will test x is equal to 2/5. If we evaluate the second derivative when x is equal to 2/5, that will equal 30 times 2/5 minus 6, which is equal to 6. This is clearly greater than 0. By the second derivative test, we can state the following. Since the derivative at x is equal to 2/5 is equal to 0, and the second derivative at x is equal to 2/5 is greater than 0, there is a relative minimum at x is equal to 2/5. The value is f of 2/5, which is negative 79/25. And we are done.